In this video, I am going to solve these three problems taken from the book Principles of Physics 10th edition, and the title of the chapter is Electric Potential. First question. A charged conducting sphere of radius 5.5 centimeter sets up a potential of 75 volt at a radial distance of 2.2 meter. So you have a solid conducting sphere which is charged. So first of all, I am going to draw the diagram for this question. So you have a charged conducting sphere of radius. What is the radius of the sphere? The radius of the sphere they mention as R, which is equal to 5.5 centimeter. I will write it clearly. .5 centimeter, and it sets a potential of 75 volt at a radial distance of 2.2 meter. So from the center of the sphere to a distance of 2.2 meter. What's the distance? 2.2 meter. In 2.2 meter distance, how much potential it sets? Exactly 75 volt. And at the infinity distance, what is the potential? Whenever you are just moving very far from the charged particle, its potential is considered to be infinity. Okay, it's zero. Whenever the distance is infinity, the potential at infinity point is considered to be zero. Now, what we are going to do, we are going to find what is the potential in the sphere surface. That means we are going to find what is the potential here, because this is a sphere, the radius is same. Am I right? If you take this one, or if you want to take this one, all the radius in the sphere is same. Am I right? So I'm going to take this as my radius. So in this place, because this is the surface of the sphere, in this point, I'm going to find what is the potential. So for this, I'm going to give a name for the potential for 2.2 meter. I'm going to give a name. So let's we take at a distance 2.2 meter, the potential is 75. I'm going to take that potential as V1, and I have to take this is R1. Am I right? Likewise, here the distance for potential V2 is exactly 5.5 centimeter. So I'm going to give this is R2, because here the radius is the distance. Understand? So we have V1 value, R1 value, we have V2 value. No, we are going to find the value of V2, but R2 value is given. So for that, we have to use the formula for potential calculation, which is V, which is equal to K Q over R. I'm going to use this formula for both of this situation. So first of all, I'm going to apply this rule for R1 and V1. So what will happen? V1, which is equal to K Q over R1. Likewise, I'm going to apply the same rule for this V2 and R2. By that, the equation becomes V2, which is equal to K Q over R2. Understand? So I'm going to name the equation as, this is my equation 1, this is my equation 2. So that means we are going to find the value of V2. So before that, better I will write V1 value. What is V1? V1 is 75 volt, and R1 is 2.2 meter, and V2 value we are going to form, and R2 value is mentioned as the R2 is nothing but the radius of the sphere, which is 0.055 meter, because I convert the centimeter to meter. Now what I am going to do, I am going to divide the second equation by first equation. So divide second equation by first equation. So first of all, I'm going to divide the left hand side of the both equation. So then the equation will become V2 over V1, which is equal to KQ over R2 over KQ1 over R1, right? If you rearrange this equation again, the equation becomes V2 over V1, which is equal to KQ over R2 multiplied by This R1 will come to the top. So R1 over KQ. So by that, I'm going to cancel this KQ, the top and bottom. So by that, the equation becomes V2 over V1, which is equal to R1 over R2. We are going to find the value of V2. So I have to make the equation in terms of V2, by that this V1 will come to the right hand side of the numerator. So V1 multiplied by R1 over R2. Now I'm going to substitute the value here. V2, which is equal to, what is V1? 75 volt. And R1 value is 2.2 meter. Am I right? What is the value of R1? R1 value is 2.2 meter. 2.2 meter, and R2 value is 0.055. So let's see what is the answer for V2. 75 multiplied by 2.2 divided by 0.055. We got 3000. We got 3000. So V2, that means the potential at the surface of the sphere is 3000 volt. Actually, it clearly shows, you have to see, when the distance will be greater, the potential is weaker. When the distance is shorter, the potential is stronger. So it's exactly proved here. For distance 2.2 meter, the potential is 75 volt. For distance 5.5 centimeter, the potential we got is 3000. So our answer exactly proves it's true. Correct? Okay, this is the answer for the first part. For getting the second part, we have to find what is the surface charge density. As we already know, the surface charge density formula is sigma, which is equal to Q over A. This is the formula. But if you want to find the answer for the second part, you must know what should be the value of this charge. Clear? Because in the question, there is no information about the charge. So what we have to do for getting the answer for the B part, first we have to find what is the answer for the charge Q. So for getting the value of this charge Q, either you can use equation 1 or equation 2. Both will give the same answer. So for our case, for my case, for my calculations, I'm going to take the second equation. If you want to use the first equation, no problem. You'll get the same answer. So what is our second equation? V2, which is equal to KQ over R2. I'm going to rearrange this equation because we are going to find the charge. Therefore, Q, which is equal to V2 R2 over K. Now I'm going to substitute the value. V2 we found in the first part as 3000. 3000 multiplied by our R2 value is 5.5 centimeter. So I have to write the value in terms of meter. So 0.055 divided by the value of the Coulomb constant K is 8.99 multiplied by 10 to the power of 9. So we'll get the value of the charge. 3000 multiplied by 0.055 divided by 8.99 10 to the power of 9. We got 1.84 10 to the power of minus 18. What's the answer? 1.84 multiplied by 10 to the power of minus 8 Coulomb. So here I use the second equation. Okay, I will show you for the first equation also. If you suppose if you use the first equation, let's see what's the answer. For sure you will get the same answer, but anyhow, I will show the calculation for you. V1, which is equal to KQ over R1, and we have to rearrange this equation. Q, which is equal to V1 R1 over K, and V1 value, which is given in the question as 75 volt, multiplied by our R is 2.2 meter, divided by 8.99 multiplied by 10 to the power of 9. Let's see what is the answer. 75 multiplied by 2.2 divided by 8.99 10 to the power of 9. Exactly, I got 1.84 10 to the power of minus 8 coulombs. See the answer? Both are exactly the same. Understand? So if you use the first one or second one, the answer will be the same. Now I am going to find the answer for the B part. What is the B part? We are going to find the surface charge density. So the surface charge density, surface charge density sigma, which is equal to Q over A. What is this A? This A is the surface area of the sphere. The surface area of the sphere, which is given by the formula A, which is equal to 4 pi r square. And we already know the radius of the sphere they mentioned as r, which is equal to 5.5 centimeter, right? So here in place of A, what I'm going to do, I'm going to use this formula. And in place of Q, I'm going to use this value. Clear? So sigma, which is equal to 1.84 multiplied by 10 to the power of minus 8 divided by 4 multiplied by pi multiplied by 0.055 square. So if you substitute the value in this formula, you will get the answer of surface charge density sigma. So let's see what's the answer. 1.84 multiplied by 10 to the power of minus 8 divided by 4 multiplied by pi multiplied by 0.055 square. We got the answer as 4.84 multiplied by 10 to the power of minus 7. What's the answer? 4.84 multiplied by 10 to the power of minus 7. What's the unit? The unit for the charge, sigma. Sigma unit is, the unit for the charge is coulomb, and the unit for the area is meter square. So this is the answer for the B part. Clear? Clear? Okay, now we have to move to the second question. This question, we are going to use the superposition principle, because here we have a lot of charges, am I right? So we have to answer one by one. In the figure, 7 charged particles are fixed in the place to form a square with the edge length of 5 centimeter. So here you have, better I will copy this picture one more time. I'm going to paste one more time. So you have 7 charged particle. Better I will draw the diagram by myself. So you have 7 charged particle. 1, 2, 3, 4. So exactly form like a square. Okay. So here, if you see the picture, if you see the figure, you have 7 charged particle, and if you see this picture clearly, you have some charges in the corner and you have some charges in the middle. Am I right? So what are the corner charges here? Minus E, minus 3E, plus E, and plus 3 are the corner charges. Minus 2E, plus 2E, and plus 3E is the middle charges. So what is exactly given in this question? Actually, here you have 7 charged particle exactly form a square-like structure, and each edge length of the square is 5 centimeter. How much work must we do to bring a charge plus 6E initially at rest from infinite distance to the center of the square? So this is our center of the square, am I right? And at a distance of infinite, you have another charge plus 6E. Now you have to take this charge and you have to bring this charge to the middle of the square. Already you have 7 charges here, and you have one more charge plus 6E, which is at rest at infinite distance. You are going to take these 6E charges from infinite distance to the center of the square. For that, how much work is needed? Why? Because already we have 7 charges here. So if you want to bring that charges from infinite, 6E charges from the infinite to the center of the sphere, you must do some work. So that value we are going to find here. So for Calculating this work, I am going to split this diagram into two parts. First of all, I am going to calculate the potential for corner charges. Potential for corner charges. What are the corner charges we have? Minus E, minus 3E, plus 3E, and plus E. So these are all the corner charges. And for this, I'm going to find what is the potential for this corner charge. And after that, I'm going to find what is the potential for the middle charges. I'm going to find the potential for the middle charge. So what are the middle charge we have? So better I will draw the diagram again. So we have a charge exactly formed like a square. And what are the middle charges we have here? We have the middle charges as minus 2e here, minus 2e. This one is plus 2e, and this one is plus 3e. Clear? And then the edge length of the square is 5 centimeters. So better I am going to take a is the edge length. So what is the value of a? Because in square all sides are equal. So here a value is exactly 5 centimeter. Likewise, this side is also a. This side is also a. And this side is also a. Clear? Understand? Okay, now I'm going to find what is the potential for the corner charge. After I found the value for this corner charge potential, I'm going to come for middle charge. Once I found the answer for the middle charge, I'm going to find the net potential by adding the corner charge and the middle charge. And after that, I'm going to use the work done formula. Clear? So let's start with the corner charge. So what's the formula? As we already know, the potential formula is KQ over R. So let's we take this is my first charge. This is my second charge. This is my third charge. This is my fourth charge. So we are going to apply this formula for each and every charges. By that, we are going to frame the equation. So corner charge potential, which is equal to KQ over R. Better, I'm going to substitute the value of the charge. What is the first charge? Minus E over R plus second charge K Q here is minus 3E over R, and the third charge plus K plus E charge over R plus K third charge is plus 3E over R. Now if you see these values, the K over R is a constant term, common term, not constant, common term. I'm going to take it outside. So K over R, which is multiplied by minus E minus 3E plus E plus 3E. What will happen? Minus E get cancelled with plus E, minus 3E get cancelled with plus 3E. But what is the potential for the corner charge? Anything multiplied by 0 is 0. Clear? Likewise, I'm going to find what is the potential for this. Potential for the middle charges, which is equal to K. So let's we take this is my fifth charge. This is my sixth charge. This is my seventh charge. Clear? K minus 2E over R plus K over R multiplied by 2E plus K over R multiplied by 3E. Again, I'm going to take the common term outside. K over R inside the bracket minus 2E plus 2E plus 3E. So what will happen? Minus 2E get cancelled with plus 2E. I'm going to write the remaining term K over R multiplied by 3E. So this is the value for middle charge. I'm not going to substitute the value right now because in the final steps I'm going to substitute. That will be easy for us. Clear? So we got the value of middle charges as k over r multiplied by 3e, and for corner charge it's 0. So I'm going to find what is the net potential. What is the net potential? Net potential, which is equal to corner charge plus middle charge potential. The corner charge potential is 0 and the middle charge potential is k multiplied by 3e over r. So the net potential here is k multiplied by 3e over r. Understand? Now we found the potential for these 7 charges. Now we have to find what is the work done for bringing this 6e charge from infinite distance to the middle. So we have to use the formula for work done. What is the formula for work done? The formula for work done, which is equal to q multiplied by the net potential. So what is our charge here? We are going to bring this 6e charge from the infinite. So in place of this charge, I am going to use this value. And in place of v net, I am going to use this value. So therefore, plus 6e multiplied by k multiplied by 3e over r. What is this r? R for middle charge. What is the r value, my dear? Half of. What is the middle charge r here for this charge, fifth charge? For the fifth charge, the r, because this is our center. So we are going to find what is this value. What is this value? This is half of a. So the a value is 5 centimeter. What is the half of a? So this is r, and this one is r. So for all the value for the r value for the middle charges is exactly half of 5 centimeter. So we have to substitute the value here r as 5 centimeter. So here 6 multiplied by 3 is 18 e square multiplied by k over r. Now I am going to substitute the value 18 multiplied by 1.6 multiplied by 10 to the power of minus 19 square multiplied by the Coulomb constant 8.99 multiplied by 10 to the power of 9 divided by half of 5, which is 2.5 centimeter. Am I right? So here I have to convert this value in terms of meter, which is nothing but 0.025. So 0.025. So now I'm going to find the final answer. Therefore, work done, which is equal to 18 multiplied by 1.6 10 to the power of minus 19 square multiplied by 8.99 10 to the power of 9 divided by 0.025. The answer is 1.66 multiplied by 10 to the power of minus 25. So 1.66 multiplied by 10 to the power of minus 25, and the unit for work is joule. Clear? And you should understand one more thing. Actually, here this R is only for the middle charge. Am I right? Am I right or not? You have to see here. This is for the middle charge. But here for corner charge, what is our answer? When you multiply this value with 0, you will get 0. But what is the value of R for the corner charge? The value for R for the corner charge is different. So whenever you get the corner charge, the value of the R is different. So how to find the value of the corner charge? If you want to find the value of the corner charge, you have to just take one triangle from here. Let's we take this is A, B, C, and as we already mentioned, the all edge length is A. Am I right? So here this is A, and all sides are A. So if you take this triangle ABC, we have to apply Pythagoras theorem. Therefore, AB square, which is equal to AC square plus BC square. So we are going to find the value of AB square. Why we find the AB square, brother? You have to see here, half of this diagonal is your R. So once you find the diagonal, divide by 2, you will get the value of the R for the corner charge. But when you come for the middle charge R value is very easy, which is nothing but the half of the value of A. But here it is different. So if you have any values, if you got any value for the corner charge, then you have to go for this method. So what is the method? Just consider half of the triangle. That means the right angle triangle, because in the square you have two right angle triangle. So I'll take one triangle ABC. Then I have to apply the Pythagoras theorem. Now what will happen? What is the value of AC? Which is A square plus BC, again another A. So A square. So the value of AB is nothing but is a diagonal. Am I right? Therefore, AB square, which is equal to 2A square. Therefore, AB, which is equal to A root 2. Am I right? And this AB is the diagonal. And then if you divide this diagonal by 2, you will get the R value. So diagonal divide by 2 gives the value of R. So A over root 2 over 2, which is equal to A over root 2. Clear? This is the value of R for the corner charge. And what's the value of A? Here A value is 5 centimeter. So you should remember these things. It's very, very important, because this question is really a very lengthiest question. For corner charge, R value is this, but for middle charge, it's a half of A. Your R value for middle charge is half of A. Clear? But luckily, our corner charge gets 0. So anything multiplied by 0 is 0. So here K value is 8.99 multiplied by 10 to the power of 9. And R value A over root 2. So if you divide this 2 with root 2, you'll get A over root 2. And in place of A, you have to substitute. So you'll get some value for R and K. But you multiply this value with 0. That's what our corner potential becomes 0. Understand? Okay, this is the method how to solve this question. In exam, we will give one of the part. Clear? Because this question is quite lengthy. So you have to read the questions very carefully before you answer. Okay, now we have to go for our third question. The third question is very easy. Again, we are going to deal with the electric potential. In the figure, what is the net electric potential at a point P? What is P? Here we have the P, am I right? And you have 4 charge particles, and all charges are exactly same. So how many charge particles we have? 1, 2, 3, and 4. And for all 4 charges, it's exactly the same value, 7.5 femtocoulomb. What is the meaning for femtocoulomb? 10 to the power of minus 15. Clear? So Q, which is equal to 7.5 multiplied by 10 to the power of minus 15 coulomb. And here the distance is mentioned. What is the distance? The distance is 1.6 centimeter in terms of meter, which is 1.6 multiplied by 10 to the power of minus 2 meter. Clear? Again, we have to find what is the net electric potential by these 4 charges at this point P. So again, we have to deal with the superposition principle. I am going to apply this formula V, which is equal to KQ over R. Here R is nothing but, for this question, it is D. Clear? So we have to deal with this formula for each charge. So let's start. So potential net, that means net potential, which is equal to potential for the first charge V1 plus potential for the second charge Q2, then potential for the third charge V3, and potential for the fourth charge V4. Clear? Now I am going to apply the value here. So let's see what is the answer. Okay, so that means this formula I am going to apply for each V1, V2, V3, and V4. Let's see what is it. For first charge we have Q. So K Q over, what is the distance between charge 1 and point P? D. Clear? Likewise, we have to find what is the potential for V2. V2 is here, that is second charge. The distance between the point P and the charge is again D. So you will get K Q over D. And for third charge, again, the distance from point P to third charge is exactly D. So K Q over D. But for the fourth charge, you have to calculate this distance very carefully. What is the distance from the point P to fourth charge is 2D. Am I right? So from the distance is exactly 2D for the fourth charge. So K Q over 2D. Now I have to simplify this question. simplify this equation. So I'm going to take 2D is the LCM value, 2D, and here you will get 2 times of Q. I'm going to take a common term K outside. So 2Q plus 2Q. And here, what is the potential? Okay, here I forget. What is the charge here? We have negative charge, am I right? So that means this one is negative Q, and also this one is negative Q. Clear? So here we got minus 2Q, and here we'll get only minus Q. Why? Because here we have 2D already. So this plus 2Q minus 2Q get cancelled, and if you simplify this, you will get only Q. Am I right? So K Q over 2D, substitute value. K value is 8.99 multiplied by 10 to the power of 9. Charge value is 7.5 femtocoulomb. 7.5 multiplied by 10 to the power of minus 15 divided by 2 multiplied by D, and the D value already given in the question as, what's the value of the D? The D value is 1.6 centimeter. Am I right? So we already have to convert 1.6 multiplied by 10 to the power of minus 2 meter. So our net potential for these 4 charges at a point P is given as 8.99 10 to the power of 9 multiplied by 7.5 10 to the power of minus 15 divided by 2 multiplied by 1.6 10 to the power of minus 2. So I got 2.107. 2.107 multiplied by 10 to the power of minus 3, and the unit for the potential is V. So this is the answer for our last question. Clear? So please memorize the formula. Without formula, it's not easy to solve this question. That's it.